Very good morning. Today I have to discuss about the Schrodinger time dependent equation. So Schrodinger time dependent equation, it is a wave equation. That is the main fundamental thing in quantum mechanics or nanoelectronics. In a classical mechanics, we know the wave equation. Any wave equation, suppose y equal to a cos omega t minus x. This is any wave equation. This wave propagate in a positive x direction with an amplitude a. With amplitude a is propagate in a positive x direction because there is a negative sign is there. If it's a positive sign is there, then it will be propagate in the negative x direction. So here y equal to s equal to omega t minus ax. Think this is the positive x direction. It's moving with amplitude a. With amplitude a. Now, here we discuss about the Schrodinger time dependent equation. So Schrodinger says any wave function we can write in this format x psi equal to x t a e to the power minus I omega t minus kx. Any wave function we can write psi x t a e to the power minus omega t minus kx. Now, here some imagination we have to, or that is you have to consider a equation. The wave is the undamped and that is the monochromatic wave. That is means its phase is constant, omega is constant, and amplitude is constant. That is undamped. Okay, you have to consider these two equations. Now, this equation and this equation, there is no basic difference because we just imagine any equation, wave equation in classical mechanics, y equal to a cos omega t minus kx. This is the natural class in classical wave equation. We just subtract the imaginary part minus I a sine omega t minus kx with this equation. Just we consider this is the real part of the equation and this is the imaginary part we have to subtract just with this equation. There is no effect of real part with the subtract of this imaginary part. Now we know e to the power I theta equal to cos theta minus I sin theta. So this y becomes y equal to a e to the power minus I omega t minus kx. So this equation can be represented by this equation psi x t a e to the power minus omega t minus kx. Just we subtract an imaginary part over here. So this is the wave equation psi x t with in a constant or undamped equation and monochromatic wave. Okay. Now here we know the wave vector k equal to 2 pi by lambda. That is the wave vector. Now, from the d wavelength, we know the lambda equal to h by p. P is the momentum and h is the Planck constant. So, we put this value here, k equal to 2 pi h 2 pi p by h, or this is the p by h line, because h line equal to h by 2 pi. Actually, we have to change this equation with energy and momentum. Energy, omega and k we replace with energy and momentum, which is measurable. So k, the wave vector, we represent here with the momentum by h line. Okay, so we replace this value by p by h line, and we also know the omega equal to 2 pi nu. And from the Einstein equation, we know E equal to h nu. So we put this value nu equal to 2 pi E by h, that is equal to E by h line. So this omega we can represent by energy by h line, E by h line. So this equation becomes psi xt equal to a e to the power minus I by h line et minus px. This is the equation number 1. So this psi xt we can transform to the omega by k by energy and momentum, and rewritten the equation, and this is the final equation of psi xt a e to the power minus I by h line et minus px. Now equation 1, differentiate with respect to time. This is the equation is dependent upon the position and time. So we have to differentiate with respect to time, that is the partial differentiation we have to do. So del psi del t has become del dt of this. That's mean e to the power means a into e to the power minus I by h cut et minus px is the same manner, and only the t portion you have to differentiate. So minus I h I t minus I e by h line. So minus I e h line del psi del t by minus I equal to psi. because this is the side. Here is the I is in the below numerator, so you have to multiply by I here. So this is I square means -1, that's means plus. So it's become I h cut by E. So it's become I h line by E del psi del t equal to psi, or E if they multiply, so E psi. This is the equation number 2. I h line del psi del t equal to E psi. This is the equation number 2. Now again, this number one equation we have to differentiate with respect to space, that is x. So partial derivative we have to double partial derivative with respect to x. So del psi del x we have to perform. It will be a e to the power minus I by h line et as well as, so it's become minus I p minus p is plus by h line. Okay, then again we partial derivative with respect to x is become del 2 psi del x square a e to the power minus I by h line et minus px. Again it's represents, so I square minus I square means I square p by p square by h line square. So this is side. Okay, so it's become I square. So it's become minus p minus p square minus h square line square by p square del square psi by del x square equal to psi. So finally it's become minus h line square del square psi by del x square by p square equal to p square psi. This is the equation number 3. So this is the equation number 3. Now we consider the non-relativistic particle is moving. So there is a speed of a particle is much less than the light speed. That is the non-relativistic particle. Non-relativistic particle is the speed of the particle is moving with very low velocity with respect to light. So in the wave theory there is a total energy of the particle E equal to, there is a kinetic energy as well as potential energy is there. So kinetic energy equal to half mv square and potential energy equal to, suppose V. Clear? Now multiplying both sides by the equation wave function psi, so it's become E psi equal to half m v square psi plus v psi. Now this half mv square we have to retain in this way, half m square by m v square plus v psi. M square v square psi plus v psi. So this becomes half p square momentum square m psi plus v psi. Now from the equation 2, the value of p psi, and the equation 3, value of the p sub psi, we have to put it here. So from equation 2 and 3, we get the value of p psi equal to what? So it's become I h cut or I h line del psi del t equal to p square psi half 1 by 2m. P square psi means minus h line square del square psi del x square plus v psi. So this is the Schrodinger time dependent equation in one direction particle, one direction moving particle. This is the Schrodinger time dependent equation. 1 by 2m into minus not plus. Now in case of three dimensional, this is the, it's become, in case of three dimensional it's become I h line del psi del t minus h line square by 2m del square psi del x square plus del square psi del y square plus del square psi del z square psi plus v psi. Or it can be written as minus I h line del psi del t equal to minus h line square by 2m so by Laplacian operator we can replace this value. This is the Laplacian operation del square. So in three dimensional case, Schrodinger time dependent equation we can write in this way. So this is the Schrodinger time dependent equation.